This discussion is going to be specific to the sensing part of the LOAF system that then sends the sensing information to the line of sight control, like Milan talked about, as well as focus control and Zernike control. June, we'll be talking about the other controls next. So I'm going to walk through a basic set of information to explain the LOAF's sensing in general, a microscopic amount about the way that the estimator is set up. The one concern that kind of stands out for the estimator, and then no big surprises, walk through some of the TVAC results. So in terms of the entire CGI optical train, what we're going to talk about for LOAFs only makes it halfway through. So at the focal plane mask, I'm going to abbreviate the mechanism is FPAM. I'm going to talk about FPM, focal plane mask, in a lot of places. That reflects light to LOCAM. And then what I'll be describing is this dark blue box, which is taking LOCAM images, deriving changes in wavefront from those images, and then passing those estimates on to the controllers. So specifically, there are 3 different actuation mechanisms that contribute to the control side of things. There's the FSM fast steering mirror, that's tip tilt. There's the FCM focus control mirror, that's focus. And then DM1 handles everything that we don't have a simple motion to create wavefront error from. So for context, we already heard a talk about phase retrieval. Phase retrieval is the way that we determine what the wavefront is. Even though this is called lower wavefront sensing, this is not what we do to figure out what the wavefront is or to make the wavefront better. What we do is we freeze it. We freeze the wavefront at whatever setting it was when we did our higher order wavefront control and made a good dark hole. So it's maintenance. It's not determining what to do. It's not investigating the system. It's just freezing. So it operates concurrently in real time, faster than the higher order wavefront sensing and control, but should be invisible to the higher order wavefront sensing. This should just keep any disturbances from making it harder to do higher order wavefront sensing and control. And then after post is done, this lets you take a long observation and maintain that contrast, not only in a mean sense, but also in a differential sense, which if you tune in tomorrow, I'll talk about that. The other thing that sort of stands out in a dual purpose context of having to do LOAFs the way we do is that star acquisition. When we say, I want to point at this star or that star, just telling, we use the wide field instrument as our guider, and just telling the wide field instrument where we want to point is not sufficient to center the star on the mask to the tolerances that we require. And so we use LOAFs as a way to do the fine pointing control that gets us centered on the mask the way that we need. AJ showed us speckle balance, which is a tweak of this fine control. But one of the first things we have to do is establish a handoff between what wide field can do and the type of pointing that we need. So I'll talk briefly about that. So what is it? So the focal plane mask itself, I'm going to talk mostly about HLC, with just the tiny scattering of shape pupils. The focal plane mask itself, solely for reasons of high contrast at the science camera, has a very fine structure, detailed thickness of this dielectric coating on the mask. This is the full size of the mask, which is about a 3 lambda OP radius. And the PMGI, the dielectric, has this pattern thickness everywhere. So people like to draw analogies to Zernike wavefront sensing because there's a good reference point to jar people's intuition. But this is a really, the structure of all this dielectric and the phase changes that it induces away from the center is a big part of a headache that I'm going to describe for nonlinearity. So the size of the PSF that's landing on this, the full width half max, let's say, is the size of this yellow circle. But as we move around, if we're off center, it's encountering a lot of extra structure that's not your simple classic Zernike wavefront sensor. But regardless, what we want to do is we want to just take differential measurements. We're looking, so this is, I want to be careful. This is at the focal plane. So there's a PSF that's, an image of a point source and it lands in one place. This is a pupil image. This is an image of the pupil along with the diffraction pattern that happened because we reflected off the focal plane mask. So low cam looks at pupil images. And when it looks at pupil plane images, the spatial structure is formed by the Zernike shapes, the Zernike polynomials that we represent phase with in the pupil. With this diffraction pattern, it looks pretty screwy. So I'm going to jump straight to the real thing. So this was, our a priori model before anything happened. A big part of what forms this is the DM settings that are in place to make the dark look dark. That as well as the structure of the focal plane mask makes this sort of non-trivial. But all we really care about is that it's identifiable. So we identify it. We actuate those different control mechanisms. So the fast steering mirror is for Z2 and Z3, tip and tilt, focus control for Z4 focus, and then the DM for everything from astigmatism, coma, trefoil, sphere. So all we really care about is not that we modeled anything correctly, but that when we actuate these phase modes, we recognize the shape that those phase modes change the intensity at low cam by, and then we use that training to reverse engineer what changes happened later. So that's the whole game. It's just training it based on what we really see, not based on what we thought we were going to see, and then decomposing everything that happens from there on as a change from the low cam image that we're getting at any one moment into a sum of these changes. So those are the coefficients that we end up with feeding the control with. There is a complication. The bandwidth of the sensor, so our optical train has its own fixed color filter that's separate from the coronagraphic image on the science camera. It's fixed. It's 20 some odd % wide. It's 128 nanometers wide, rounding here a bit. And the detailed morphology is a function of wavelength. So when you illuminate it with a star with a red spectrum, you'll be predominantly looking at the morphologies on the red end. And when you illuminate this with a star with a blue spectrum, you'll be predominantly looking at the morphologies from the blue end. And so those changes in these morphologies with wavelength are something that we don't do the right way in testing. There are telescope simulator, CBS, doesn't have a good way to modify the spectrum other than cutting chunks. All it can do is put in a long band pass field cutoff and a short band pass cutoff, but it can't change the spectral slope. So it's a big test as you fly exception, and that means that a lot of our requirements are verified by us. I'll have a little more to say about that. So in cartoon form, the full version of what we try to say is we take as I said, we want to freeze the wavefront. So we declare one low cam image as our reference. And we say, that's the one I want to freeze the wavefront at. And then I form all my differential images empirically. I move all the fast steering mirror, the focus control, the DM, and I see what happens. This one is a purely camera-based nuisance that we want to take out. That's what if just the overall uniform bias across the entire image changes. That's not a real signal, but we don't want to be confused when that happens. There's a certain amount of calibration of what we expect the flux to be, and we can be wrong. So we want to soak up those errors purely as an error in what we calibrated and not misinterpreted as the different Zernike coefficients. So we fit for that. We fit for errors in the flux separate from the other coefficients. And then camera shear, if the image at low cam, which is a pupil image, moves. If the image moves, that's not an interesting optical effect, that's a nuisance. And so we separately solve for that and don't get confused by it. I'm not going to go through the math. So the complication that I mentioned before is nonlinearity of tip tilts. And if you remember that focal plane mask image, there was a ton of structure where the PSF, that's an image of a point source, lands in one spot on the focal plane mask. It's not a simple Zernike wavefront sensor. As you walk off center, you're getting a whole different diffraction pattern. So again, not to be confused, these axes are where the star lands on the focal plane. These are not pupil plane images. They're also not really source images. These are where did the star land on the mask and what did the estimator produce when the star landed at that spot. If this were linear, this is the Z2 estimate, this would just be deeper and deeper red the farther you move right, no dependence on Y, and deeper blue the farther you move on the left, no dependence on Y. It would just be a ramp that goes on forever. Same thing for Z3, it would just be a ramp. More the farther up on the mask you land, Z3 estimate you get, and vice versa. The fact that there's so much structure in this estimate is the nonlinearity that we have to be sure we still function under. So the complication is that there are two very different scales. When the loop is closed and we're just sitting there dealing with ongoing disturbances, we only wander by a millisecond RMS in each axis. And on these scales, this is an 80 millisecond radius circle. So this is not even one of my pixel samples of this resolution. So when the loop is closed and we're sitting there, the linearity is fantastic. We're just barely wandering by less than one of these samples. So that's not a problem. But what I mentioned before about acquisition is we need to get to that point by letting the line of sight loop control do its thing, by taking these estimates, feeding them back, and driving it closer to the center. And so that's the part we need to test, the part we need to worry about. Milan already showed the good answer, which is that for the most part, that works. There's a little bit of concern that we may need to, I don't want to speculate too much about whether it needs to change or not, but this is the big concern, is this nonlinearity of the tip tilt estimates and whether capture really works. So I'll come back to that. The proof is in the pudding. If the estimator is giving good estimates to the controllers and the controllers work, that's where the rubber meets the road. And so I'm just going to kind of zip through these. Milan already showed all this. This is just to say that the tip tilt control was tested and meets its requirements. There's focus control, it was tested and meets its requirements. There's the Z5 through 11 control, it was tested, it meets its requirements. This is more of the Z5 through 11. So the good news is that when things are good, things are good. So the remaining question is, for this capture question, where we need something to, I will wrap up shortly. The concern was over the nonlinearity in the tip tilt estimates, the fact that these are not simple maps that let you drive straight home. So instead of driving straight home, this is a model expectation of, if I put the star, so again, these axes are where the star lands on the focal plane mask. So if I put the star on the focal plane mask at any one of the starting points of these squiggles, they will follow the gradient of the estimator, not the real offsets, but they listen to the estimator. And in the model, everything found their way. Obviously, this is worth testing. And I may have misquoted some of the high-level summary of Milan's work. My understanding was that a couple of points needed retries. These are Milan's data, and he'll be the right person to explain how they fit into the big picture. But that some of the starting points required a retry and succeeded on a retry. So if we find ourselves struggling with this issue, there are flight software solutions to this. Milan mentioned, there was a testing concern of wasting time or losing time because of fault protection responses, the way things are currently set up. But all of that can, if we find ourselves having trouble with this in flight, all of those things can be changed by flight software. How painful that'll be is a different question, but fundamentally, this is not going to prevent us from succeeding in all the other ways. I'm going to just cut it short. We did do tip tilt calibration of the shape pupil modes, and we did operate the wide field of view mode with the tip tilt. We operated HOPES with the tip tilt loop closed for 8 hours and saw no issues. So, it's encouraging, but it's not a full suite of tests. There are wavelength dependencies that I mentioned earlier. These pictures don't quite do it the differential justice that you need to make quantities out of it. And we really haven't done the model validation of the chromatic issues that it would take to say how much of a performance issue it'll be. So we verified our requirements by analysis. There's further model validation that we took data to then use. We can do further model validation with data that we took, but we haven't done that analysis yet. And I'll end it there.
Yeah, Brian, you mentioned the chromatic effects, like different stars of different spectral types, like would force the lobes to change shape, so if we maintain it on a bright star of type O and then we move to an FGK target star, we don't want actually that same solution on the lobes. So how do we deal with this, and how big is the effect?
Yep, okay.
How big is the effect?
So the effect, there's two levels of attention we pay to these effects. One is the requirements level at TTR5, and all of these things are spectacularly fine in that respect. If we ask the sort of more optimistic question of, let's say that the observatory is as fantastic as the models say it will be. Let's say that our own, once we're not only asking what can I do in 10 hours, one shot with a super bright planet, and I'm asking fainter targets and longer integration times targets, then this does become a large factor. So I didn't answer your first question of to get to the punchline. This may well be the dominant factor given the operational scenario we have for lobes in the optimistic case. How we deal with it is very simple. We train ourselves on our reference star, which is blue. We ignore all of these effects and just live with the consequences. So that is the baseline that we've evaluated our performance against. And the question of okay, fine, if that's our limit, how would we do better? There's some question as to whether we can trust some of the TBAC data that I'm showing right as we speak, where we had the option of doing wavelength resolution. So, the numbers say the story here. We used the short and wavelength cutoffs to give us spectral resolution, broke our band into 5 different chunks, and we can measure this. If this were repeatable in flight, we could, do an offline calculation to do a better job. So just to put the numbers in perspective, the 0 point change that comes from saying, oh, my lobes reference, the thing I look at on low cam and say, I need to drive that back to what I saw earlier. When you're looking at a red star image and trying to drive it back to a blue star image, you will drive the tip tilt away from zero. You'll drive it to a different spot. And the tune of that is about 0.2 milliarc seconds. And when it's systematic, so we got a 1 milliarc second residual jitter requirement that we're perfectly happy with. But when it's systematic and it's always 0.2 milliarc seconds, the average is 0.2 milliarc seconds. That can actually be our limit for the optimistic case. So we don't have a plan to do better than that. I would be, kind of excited if we get to the point where that's our limiting case, because that means we're doing pretty well. And the path forward from there is a little bit touchy-feely. We'd have to see how much we can understand about whether the spectral dependence in flight looks just like we calibrated on the ground, and how much we can sort of pre-calculate what offsets we need to do better in flight.
Sure. Thank you. Any other question for Brian? All right, thank you, Brian. Let's move on to the next talk.